Hold on tight, because we're going to show you a whole new dimension of the black giants in the universe. Can you believe that there are enormous black holes in space that science theoretically knew existed long before they first saw the dark? Giants with their own eyes? It's been 100 years since the first black hole photo was made public. In 2019, scientists around the world held their breath due to the mystery surrounding black holes. A very special chapter in astronomy reached an unprecedented climax when NASA announced the first real image of a black hole. With these images, what had been only a guess or numbers in mathematical equations for nearly a century became visible to people's eyes for the first time: a massive black hole at the center of a galaxy. Let's take a look back in time a little. Humans have been observing stars since the first time we looked up at the night sky, but they could never have predicted the abundance of amazing and enigmatic phenomena the universe actually contains. However, some astronomers had amazing knowledge of objects long before they were visible through telescopes. In 1783, British priest and ardent astronomer John Michell had a vision while gazing up at the night sky via a still relatively simple telescope. Suddenly, John Michell thought, or possibly knew for some reason, that there might be something in the universe so enormous that they would bind everything to themselves and eat light. He named these eerie phenomena dark stars. Moving forward, almost 130 years later, German astronomer and physicist Carl Schwarzschild published a paper shortly after the war describing a completely collapsed object of immense size. It's truly amazing that Schwarzschild was able to predict even the event horizon of a black hole using only mathematical formulas. In 1917, while the trenches of World War I were in flames, they were wondering how to solve the unanswered questions of Einstein's field equations. In 1931, Indian physicist Subramanian Chandra Shekhar added another piece to the puzzle by describing, in rigorous terms, a boundary surface behind which light could not escape from the black object. Chandra Shekhar discovered the gravitational collapse limit. The astrophysicist demonstrated that stars that surpass a specific mass threshold collapse due to their own gravitational pull, resulting in the formation of the very completely collapsed objects, or black stars, that we now refer to as black holes. This limit, from which stars collapsed to black holes rather than neutron stars, is known as the Chandra-Shekhar limit. The term black hole was not used until the 1960s after a scientist became tired of referring to the still purely theoretical phenomena as completely collapsed objects of large size in a somewhat convoluted manner. In 1963, the time had initially only one powerful X-ray. In the binary star system, the source was located. Researchers thought Cygnus X1 was a binary star system based on the data, but when they found an initially unreal huge star with a brilliant glare and an invisible companion, they began to suspect that the invisible companion might be a black hole. In the 1970s, the remarkable discoveries surrounding the black giants continued, and calculations led the researchers to the conclusion that there must be active galactic nuclei. The theory was based on the observation of strong emission sources in the centers of some galaxies known as active galactic nuclei, or AGN for short. These were soon linked to black holes, and more specifically, researchers assumed that the extreme energy releases could be caused by the accretion of matter around supermassive black holes. Shortly after that, the observation could be confirmed, what Mitchell, Schwarzschild, Einstein, and Chandra Shekhar could only speculate. We have also known since 1994 that our galaxy has a supermassive black hole. Once more, the Event Horizon Telescope provided us with this view of Sagittarius, a star in the Milky Way's core. The weird twin Cygnus X1 has been the subject of scientists' attention for decades, and the odd observations haven't stopped for some time. Researchers believed that the black hole was consuming matter from the blue star's outer layer. As matter falls closer to the black hole, it gets very hot and releases X-rays that can be picked up by specialized telescopes. This is also how the white and black star binaries were discovered. An X-ray telescope initially detected the signals. Large portions of Einstein's theory of relativity have finally been confirmed, thanks to the discovery and observations in Cygnus X1, which not only marked a significant advancement in the search for black holes, but also gave researchers exceptional observational opportunities of a truly unique double this close to a star. Astronomers were able to better study the properties of a black hole because black holes themselves are not visible. Rather, they become perceptible because they affect the matter around them in very specific ways. The more mathematical assumptions are verified by actual observations, the more confident researchers are that they can uncover the deepest secrets of the universe in the star system. Researchers at Cygnus X1 witnessed firsthand how a black hole's immense gravitational pull accelerates a star, causing a Doppler shift in its light that can be analyzed to determine the mass of the black hole. Gravitational lensing is another technique to find black holes. When light from a far-off object approaches a black hole, the black hole's gravity bends the light, creating a distorted image of the object that can be used to verify the existence of a black hole. Even though we now know a great deal about black holes, there is still a lot we don't know. Black holes can be found in almost as many different types as bright stars. In fact, the Milky Way may contain up to 400 million of them, and at least 2 billion galaxies in the observable universe have supermassive black holes at their cores. Every one of these black holes is distinct, with its own set of laws and gravitational attraction. The greatest black holes are 1 million times heavier than our Sun, while the tiniest have 3 to 4 solar masses. 3 layers make up a black hole's structural makeup: the singularity, ergosphere, and event horizon. The event horizon is a black hole's outermost layer, a hypothetical line delineating the location of the escape. Within the event horizon, velocity exceeds the speed of light, making it impossible to avoid the black hole's gravitational pull. Light, and all other objects, are inevitably drawn inward. The ergosphere envelops the event horizon beyond this line. Theoretically, it would be feasible to use space-time to extract energy by making matter spin in this area, because the black hole spins so quickly that even space and time are swept along within the ergosphere. This phenomenon is known as the Penrose process, and it may serve as an inspiration for new energy sources in the far future. Singularity is a black hole's presumed center, since no one has ever looked into a black hole, and it is highly doubtful that humans will ever be able to do so. Scientists assume that the entire mass of a black hole is concentrated in an infinitely small and dense region in the singularity. The space-time curvature and gravity are so extreme that the laws of physics as we know them no longer apply there. However, there is some hope, because Hawking radiation is a minimal light emission in which quanta escape from inside the black hole and then spread out in space. These quants remain forever entangled with their partners inside the black hole, and may eventually serve us as useful sources of information. 3 primary categories of black holes are distinguished from one another. Black holes in stars. Black holes, both primordial and supermassive. When a huge star dies in a supernova explosion, it falls under its own gravity, creating a stellar black hole. Black holes usually have masses between a few and tens of solar masses, and the mass of the ensuing black hole is determined by the mass of the initial star. Primordial black holes are thought to have formed in the early stages of the universe shortly after the Big Bang. They would have been the result of density fluctuations in the cosmic background caused by quantum mechanical effects. Supermassive black holes, which are found at the centers of galaxies and have masses of millions to billions of solar masses, are thought to have been formed by the coalescence of many smaller black holes and are instrumental in the assembly of stars in the form of galaxies. Since the James Webb Space Telescope has been in use, primordial black holes would have a vast variety of masses, from microscopic microblack holes to gigantic objects. Just a few 100 million years after the Big Bang, scientists found very old black holes that were already at the center of fixed and extremely luminous galaxies. Since then, the theory of primordial black holes and the Big Bang itself have been tested. After a star collapses, a relatively small black hole is initially formed, but over centuries, black holes wander through the universe and meet other black holes. The giants magically attract one another and can then merge. This fusion releases a huge amount of energy in the form of gravitational waves, and the black hole that results from the fusion has a much greater mass than the sum of the original black holes. It will likely take scientists decades or even centuries to fully understand the enigmatic giants in the universe, and in the meantime, new discoveries keep coming up that raise new questions. To date, researchers have not yet discovered everything. They need to know about the formation and growth processes of black holes and how they affect the current structures of the cosmos. The Event Horizon Telescope's 2019 direct sight of a black hole was only the beginning. Researchers are now collaborating with a global network of radio telescopes to find further black hole images. We can still wonder when science will eventually be able to make black holes directly visible. Perhaps it will be possible with the use of specialized filtering techniques. The image of the supermassive black hole at the center of galaxy M87 essentially depicts the bending of light caused at its event horizon rather than the black hole itself. How do you feel about these actual images of black holes? Do you also believe that they mark a significant advancement in space exploration